Welcome back. Today we are setting upon the long and winding road of making a titanium Damascus katana with Damascus steel core and cutting edge. This is going to be a tough one, but let me tell you why I want to do this. 2 years ago, upon discovering that the patent for making titanium Damascus had expired, I decided that it was time to figure out how to do it. And we were successful at making beautiful patents out of titanium that reveal colors that are so unique and only possible with this incredible material. Just look at it. Isn't it wild? Titanium is the metal of the space age. Its incredible strength to weight ratio means that it is the material of choice when performance is required and cost is no obstacle. From the SR-71 Blackbird to pistons in racing engines, I drop forged that out of titanium, to hip replacements thanks to its low reactivity in the body. Titanium is an incredibly special metal that is very challenging to work, but it's even more challenging to get it to bond to steel. And so over the course of several months in 2024 and 2025, after doing reams of research, speaking to experts, and with experiments here in the workshop, we successfully diffusion bonded, otherwise known as forge welded, titanium to steel, and I was able to create a direct bonded titanium and steel chef's knife, as well as a nickel interlayer diffusion bonded titanium Damascus to Damascus steel axe. And the dream throughout all of this experimentation and research was to start what we are starting today, a titanium Damascus katana. The history of the katana as a weapon, a tool, a piece of art dates back to the 4th and 6th century in Japan, and for over 1,000 years the katana was at the forefront of metallurgical innovation across the world. What those blacksmiths discovered and understood about steel making and metallurgy is truly remarkable, and with the greatest respect, I want to produce a piece of art that is a fusion of this historic symbol with modern materials. And in order to pull this off, we're going to need to do reams and reams of experimentation, research, and trial and error, and that is going to begin right now. Though I have forge welded titanium to steel successfully, I have only done it on rather small pieces. But a katana is much larger than a chef's knife or an axe. When things get long, they get wobbly. When things get wobbly, they can bend. The challenges in making a forge welded and laminated sword of any appreciable length are so much greater than something short. We're going to be fighting cracking, warping, challenges of trying to get the hardness that we require. This is going to be an enormous undertaking. Thankfully though, we do have a reference to use as an example. A couple of months ago, a package arrived from Sordis, who is today's sponsor. I was able to go on their website to use a katana builder to get a custom-built katana to my specifications. And what's awesome about this is it is the experience of getting a custom sword without having to pay the price tag. They collaborated with 3 katana brands where you can now pick between 27 different options, like tens of thousands of combinations here. And the result is incredibly impressive, especially when you consider the price tag, because you wouldn't be able to have this experience for this cost with an individual sword builder. I was able to select everything from the point or kasaki that I wanted to the hamon type, the steel used, the Tsuba, Habiki, Seppa, and all of the other fittings. And when you look at the profile and shape of that, and you imagine that I need to make this out of titanium Damascus and steel Damascus, it is daunting, because it is long, thin, it needs to be perfectly straight, and it needs to have all of the mechanical and physical properties that we require. Go try using Sordis's custom katana builder. It's really interesting to have a play with. And if you use code ALEC10, you'll get 10% off Shadow Dancer custom katanas. We appreciate them sponsoring us, and this is going to be a fantastic reference to have in the workshop, along with thousands of pages of these books that we need to go through to make this project as good as it deserves to be. And so with that, we need to come up with a bonding plan. Now, the laminated construction we're hoping to achieve absolutely has historical context to it, but which of these styles we actually use is going to depend on the results of our following experiments. Rudolf Dick's book on Japanese blacksmithing is fantastic, and I definitely recommend it. We need to go shear some titanium and steel. Yeah, boy! This is our titanium. Get some steel for a jacket. Oopsie. I mean, this is a 2-man job to set this up.
Too bad I'm a lady.
Let's go! All right, so for our first 2 experiments, here's my steel. Here is all of my grade 2 titanium. And here is my jacket material. Now you'll see, for 2 billets, I only have 4 pieces of jacket material because in order to reduce the amount of welding on the jacket by 2, I want to make it into a U shape, and so I made a die and a little top tool to do just that. I've given it all a test, and in theory, it should work just fine. That looks a bit crap. Golly, that's quick. There we go, you are now looking down the end of our first 2 experiments. As you will see, we've got on our long and thin billet, titanium, nickel interlayer, steel, nickel interlayer, titanium, and our short and fat has titanium, titanium, nickel interlayer, steel, nickel interlayer, titanium, titanium. Should be obvious now what we are trying to test. We're trying to test if it's going to be better to bond these materials together in a thinner but longer profile where there is less drawing out and forging to do, or whether it's better for us to bond them together in a short and fat profile. I've used a thicker steel in our short and fat piece so that when we draw both of these out to about 900 millimeters, 6 millimeters thick, our short and fat piece is half the length and twice thickness, and of course with a thicker bit of steel inside it so that hopefully the core on both of them of steel, when they are drawn out to 900 millimeters, is consistent between one and the other, and we can see if we learn anything. It's going to be very important for me to decide if I'm going to do the bonds for our katana close to final dimension or a long way away with lots of forging to go. Both of our samples have a 0.2 millimeter thick nickel interlayer to act as a diffusion barrier between the titanium and the steel. We're going to weld a little end cap here with a hole so that the argon can flush through. We're going to weld some pipes on this side so we can hook it up to my argon hose, and hopefully we're going to be learning a thing or two pretty quick. There's our argon. Plug that in here. And what we're doing, we are pumping argon through this billet so that we're hopefully going to evacuate all of the oxygen. I can then turn the pressure down and just have a little trickle, so we've got a positive pressure in here. Any oxygen in here at a high temperature is going to be a bad time because titanium oxidizes very strongly at temperature. Oh, hello. We're definitely getting argon flow. We've now turned down the flow. Okie dokie, 900 degrees Celsius. 1, 2, 3, 4. Ow! Yeah, baby. Yeah, mama. Let that sit in there for a minute. Then we can pull it out to air cool and start on the next one. Unfortunately, there's no real way to know if oxygen's in it or not. We just hope and pray. In we go. Up to temperature. Here we go. Once these have cooled, we're going to peel off the mild steel jacket, which shouldn't be bonded to the titanium. We'll see if we got welds before we then draw it out to final size. Oh yeah. Oh. Oh. Woo. One down. Now remember, the reason this mild steel jacket is coming off of that titanium so easily is exactly why it is so hard to forge weld titanium to steel. See, what's happened here is when we heated up our titanium and we heated up our steel and we smashed them together, the iron atoms and the titanium atoms, they reacted to form what's called an intermetallic compound. So instead of just bonding together, with that temperature, they were able to react and form something completely new. And it's this light gray that you can see on this steel here, and that intermetallic compound of titanium and iron is super, super brittle. It isn't strong enough to be able to hold a katana together, as you can see, because we're ripping it apart right now. That is exactly why we put a layer of nickel in there. That is what's called an interlayer, and as I mentioned earlier, it's a diffusion barrier, so it stops those iron atoms ever reaching the titanium atoms. Nickel likes to bond quite well with titanium, nickel also likes to bond quite well with steel, but it keeps them both nicely separated. Now, I have been able to successfully weld titanium to steel without the use of an interlayer, and I made a chef's knife with that technique, but that involved keeping the material at temperature for as little time as possible. So heating it up, smashing it together to bond it, and then immediately quenching it. And that is an idea that I was given by Professor Amir Shehzadi, who is an expert in the field of diffusion bonding and has spent his whole career working on the topic. And so the reason that I chose to not go for a direct bond but go for the nickel interlayer is so that we have the ability to do what we're about to do, which is heat them back up and forge them out to final dimension. Oh, look at that! I picked up a boo-boo.
Boo-boo.
A boo-boo. I think I've just given my wife the ick. Check this out, though. What? Damascus steel band-aid. Look at that. I am now part Damascus. Now, the thing is, now that these pieces are all bonded together, no more oxygen can get inside there, which means we can crank the temperature, go a little bit hotter, forge them out without the jacket or the argon shielding. So we can now go up to 1,050 degrees Celsius. Okay, start on the thick one. Oh, yeah. Oh, no! Oh, no! That's not good. Oh, boy. Oh, it's awful. Look at all the stuff that we just squished out. That, unfortunately, my friends, is that intermetallic compound, which the only reason I can think for how that's happened is that the edge of the steel has kind of folded out past the interlayer, just on the edge, and touched the titanium, reacted with it, forming that intermetallic compound, and then, guess what? That intermetallic compound has a lower melting temperature than either steel or titanium. Steel melts at like 1,500 Celsius. Titanium melts at like, on a day like this, room temperature, so even hotter than steel. Bugger! Look how brittle it is. That intermetallic compound melts at a much lower temperature. So that sucks. Let's not talk about the amount of time that it took to get that sample to this point for the experiment. What day of the week is it? Oh gosh. It's the end of the day on Thursday, and we started this on Monday. Now, admittedly, our efficiency has been a little bit reduced by the increased temperatures. That is such a shame. Nice experiment, Alec. You melted your sample. Well, I'm going to do the next one at a slightly lower temperature. I'm going to do it at 1,000 degrees Celsius, so hopefully we don't get anything squidging out. We'll continue rolling out the other one, because, I mean, what else are we going to do? We'll still get them to an even size, but it's going to be interesting to see what happens. Let's see how much we lost. We've lost about 90 grams, which is not insignificant. Here we go. 3, 2, 1. Oh, no! Oh! Oh, hello. That's a disaster. It did it again, even with a lower temperature. This is a real problem. I wonder if it's maybe has something to do with the rolling. I mean, why would it respond differently to rolling as compared to hammering? I mean, I've done this before. This is not the first time we've forged titanium that's welded to steel. Why is it being weird? I just don't know what's going on, guys. Okay, we'll do this one. That one's better. You know, apart from the whole, like, banana-ing, that one went a lot better. That's a much lower temperature. Okay, 950 Celsius. Much better. Another one at 950. God, even just getting this stuff straight while it's hot is next to impossible. Goodness gracious me. It's not looking good. Let you slow cool there. Quick recap. Upon taking them out of the furnace at 1,050 degrees, we discovered, fortunately only at moderate speed, some liquid intermetallic compound. I'm a bit concerned about how that could have formed. Maybe we were deforming it too quickly and we like ripped apart the nickel interlayer, exposing the hot titanium to hot steel. Maybe it was just the edges where there could have been some overlap and the titanium could have touched the steel. I'm not entirely sure. 950 degrees Celsius seemed to be an appropriate temperature where I could still do a little bit of rolling and reduce the thickness, but we didn't get that sludge. Now then, subsequently trying to straighten these things after the rolling was a good bit of a challenge. I'm gonna leave them in the kiln to cool down overnight and have a look tomorrow. I am wondering a number of things. And I'm quite scared because I've set out on the project of making this titanium Damascus katana. The prospect of actually being able to pull it off is starting to be quite concerning, and here I am. I thought it would be challenging, but I kind of thought like I'd be learning things along the way with moderate amounts of success, and then kind of refining our way to success. But currently it seems like, it's just failure. And failure is the least satisfying way of learning things. Looks like there's a delamination there on the top piece. Oh, it's definitely come apart there. That's not good. We don't have to be metallurgists to know that that's not right. How wild is that top one? You can see the gaps where we squidged out that titanium iron intermetallic compound. Look at how much of the thing we've lost. That is no bueno. The bottom one is a little bit better, but there's still some of those little holes. I mean, that is a colossal failure. The steel is fully detached from the titanium, or the interlayer even. That is bad, and this is the better one. Look at that disaster. Oh, goodness. Yeah, can't make a katana out of that, can we? Yummy. Great. No big surprises there. Oh, hello. Ripped straight apart. Oh, gosh. That's not meant to happen. It's not looking good, guys. Those voids from the material squidging out made a stress concentration that broke the steel. And on this one, it fully delaminated. Interesting. That wasn't a very good few days in the workshop, was it? In the scrap with them. All right. This is some sheet from some of the experiments in 2024. And here, some of the old test pieces. Also got some here. To match, we're looking for number 3. This old fella. Put you in there, guy in 2. So I've taken those 2 samples from a couple of years ago and put them in the kiln. So one thing I recognized is that when I made that titanium Damascus axe, I actually only forged it during the welding heat. So I didn't do any further forging after the fact, and it was always in an argon canister for that single welding heat. So between it and these experiments, I actually changed 4 variables, not the 2 variables I was hoping to change, which was just the dimensions of the piece. So that's some pretty shoddy experiment design on my part, which I'm paying the price for. But hopefully what we can find out now, with these successfully bonded pieces that also had a nickel interlayer from a couple of years ago, can I then heat them up without an argon jacket and then actually forge them without them coming apart? Was that the crux of this whole issue? Wow. I think I could have tightened the rolls a bit, eh? Whoa, hello. Yeah, that just ripped apart. Next one. Hey, that one stayed. There's the first one, it doesn't look very good at all. We're gonna try hand hammering the other one. Okay, back in the forge. Second heat. Yeah. And by yeah, I mean nah. Definitely appears we can't forge that, as it appears that nickel has separated from the titanium, which is not ideal. So I think it's pretty clear now. Forging bonded titanium to steel, significantly changing the cross-section, is going to be a no-go for us. So as annoying as it was to throw a week's work in the scrap, I've definitely learned something, which at the end of the day is the goal of experimentation anyway. And the answer to the question of whether we go long and thin or short and fat before we forge it out is neither, because we can't forge it out. All that we can hope to do is take our material, bond it at full length, and that's it. Finito. It would then be a case of heat treating the steel, cutting out the blade profile, but this of course needs experimentation. Will it actually work? Because this now means that everything starts much longer. We'll have to weld way more material in one heat, and my oven is about a foot too short. And so for our next experiment, we're going to use the longest billet that we can fit in the kiln and test the material after one single heat of bonding. All right, in a little bit more on your corner, like a smidge when I say in. Well, I guess you can also use your eyes and line it up, eh? Fingers clear, cutting.
What? What? Take that pen out of your mouth.
Please, can you turn on the fire?
Turn on the hammer.
You know exactly what I am saying! Okay.
Did you say you?
No, stop!
Oh.
What the
Bellissimo. Oh, I love that for me. It doesn't fit. Ah!
See, what I would have done is made that swage die the same thickness as these, and then it would fit.
Oh my goodness.
They fit like a slightly tight glove. In fairness, I like my gloves to be tight. I don't like loose gloves. Who wants a loose glove?
Where'd that bit of steel go? Somebody keeps moving it. How is it longer? Where did my measurements come from?
Your brain.
I'm very confused. Yeah, that would do it. I changed my measurements halfway, and then I didn't remember them. Okie dokie. In we go. All right. Here we go. All right. That is hard when it's that long, and it is also very wide. This is part of the big concern about this is it's so long, it needs to be at temperature. I went for a slightly lower temperature of 850 Celsius, which is the same temperature that we know worked well on my titanium Damascus axe, but it's very long. It's also 3 inches wide, which is as wide as our final billet would need to be if we were to make a katana with this technique and cut it out. Trouble is, the longer it is, the more distance I've got to cover with my hammer strokes. The wider it is, the less the actual pressure on the bonding interface. Because obviously, pressure is a function of the cross-section that we are hitting on. This is significantly wider. It's significantly longer. And we've only got 1 heat to pull off these bonds. And by goodness, it cools down quick. A bit nervous about this project, Jamie. A bit committed now.
For all you know, there's a success in that kiln. You just got to wait for it to cool down and find out.
Yeah. But I will still need to make it about 30% longer on the final thing. So it's still not like an exact replica of our final processes. And I feel like I was pushing the limits of what I can bond in 1 heat there, if it bonded.
So are you saying in this instance, longer isn't actually better?
I'm saying longer is a lot harder to deal with.
Well, yeah, I mean, that's what you said. We have a leak.
It has grown legs, one, because it is now no longer square to the massy.
And it's also inconstant. Is that the word?
Incontinent? Yeah, I think incontinent.
Anyway, wheeze all over the
Inconsonant
floor.
would be like a grammatical thing. Incontinent would be a bladder holding thing.
Right, okay, well that's what I meant, yeah. And if you look in here, you can see it's like a swimming pool
Yeah.
of oil.
And I forgot to bring my bathing suit this morning.
Your bikini?
There's also oil on top of this, Jamie. And if there's oil on top of that, it could be leaking around this fitting. It's not moving. Nothing's moving. I think this is like a radiator, and it appears to be filled with oil. That's not good. Maybe I overfilled the thing. Oh, look at that. It's perfect. It's not bad.
Yeah, well there's nothing in it because it's all on the ground.
Ah, at last I can see inside my press. These pipes to recirculate the oil are completely full, which is probably not ideal because I presume it's a low pressure recirculation of oil. I wouldn't assume they should both be full. Oh, that's not solid. Oh, you know what we could do? We could drain out some of the oil of the tank and see if it drops the level here. God, delightful. Oh, yummy. Look how clear looking that oil is. The level is dropping. Great news.
I stood up too quickly and I think I'm gonna pass out.
Ooh, yes. It's like a wave machine at your local swimming pool. Oh, there goes my t-shirt. God, thank goodness I know just where to buy more of these.
At asteelblock.com.
That's the one. We've got our Damascus pattern t-shirts on the website now.
So that pan is supposed to be for catching the oil.
Yeah.
Yeah, just letting you know.
Are we getting a hamster?
We'll find out if that leak got resolved in a couple of days. For now, let's get this jacket off. Oh, yeah.
Yeah, it's quite promising.
Have you just jinxed it? The blame's going on you, Popple. Oh. Does it sound like it's cracked? It rings like it's one piece.
I think it's bloody worked.
Might have blooming worked, eh? It might have worked. Let's see how much strain we applied during the bonding. How do you think we might figure that out, Jamie?
It's how much you moved the material compared to what it was in the first place.
Yes, exactly. It was 12.2 millimeters. It is now 11, 11, 11.1, now 11 millimeters. Difference is 1.2 millimeters. Strain is 1.2 divided by original length, which means we applied 0.098 strain. We basically squished it 10%. Is that enough to get these bonds to stick? In industry, when diffusion bonding is done, they're often aiming for very, very, very little strain because it changes the cross-section of the part. But they're also doing the bonding over a significantly longer amount of time. So they might be holding a part like this under pressure at temperature for like 2 hours. Here, I've got like a few slaps on the hammer and that's all we've got. So we've got to use a lot more force, and also more force means more strain, more squish. Right, you know what this is, Jamie? This is all distracting us from what we actually have to do, which is, what do we actually have to do?
I don't bloody know.
Well, I guess we've got to test it and see if it's proper. So, I think I'm gonna mill the edges so that we've got some nice clean sides, and then we'll section off some components that we can test individually, and then we will harden a good chunk of this.
What the was that?
What the hell? I just snapped my first 12mm end mill. That's the biggest end mill I've snapped in my life. We totaled that thing. Do we see any delaminations? Both sides, under simple visual inspection, nothing, which is exactly what I want. It looks good to the naked eye. How about to the Temu microscope?
You've got a very expensive microscope in the office, you know.
Why does it not turn on? It really needs to charge while it's plugged in. Here we go. How about this one? Needs to charge too. I really want a metallurgical microscope. I'm always looking on eBay, but I also don't want to spend £1,000 on one. I'm trying to find a deal on one that's like been dropped a couple of times, you know what I mean? Right, now we've got it under the microscope, powered by apples. Interesting, there does appear to be a little line between the nickel and the titanium that I don't like the look of. There's less of a line between the nickel and the steel, and there's no line on the right-hand side. Yeah, I don't like the look of that line, do I?
You tried smelling it?
Smells half stuck to me.
Does it smell solid, or does it smell like number one? Fancy t-shirt you're wearing there, by the way.
Oh, well, thank you very much. Now available, asteelblock.com. I'm going to cut this off about there so that we can take some little sections down that piece, do some further experimentation, and then with this large piece, we're going to try and harden it and temper it and see if it pops apart then.
You're nuts, you are, man.
How's that nuts?
That's Rocky Mountain oysters trying to cut through that.
Did you look it up?
I had some last night.
Yeah, baby! These are our 3 samples to do some tests with. Gone ahead and hardness tested one of these. Comes out at 26 Rockwell in its unhardened, air-cooled state. With those 3 samples, the plan is going to be as follows. With 1, we are going to oil quench it. We want to see if it will get hard enough, or we want to see if it splits apart and delaminates. 2, I'm going to take one out and just simply air-cool it, see how much hardness we get from an air-cool, now that it's a slightly smaller cross-section. 3rd sample, I'm going to take to the rolling mill. Remember, it was 12.2 millimeters. We bonded it. It then became 11 millimeters. My plan is to apply approximately 0.1 strain with each heat and see if maybe at a lower temperature of our plant, 850 Celsius, and with pretty low strain per pass, is it forgeable now. First one's air cooling. There we go. Let that air cool there. Oh, so pretty. Wow. Look at those strange squiggles. Next one's quench. This is our quenched sample. It appears to still be in one piece. Can't see any cracks yet. Definitely hard, because it does not grind very easily. It looks good. Ooh! 62 Rockwell. 65. 63. Very adequate hardness there after the quench. We are obviously using a knife steel 1080 as the core here, but part of the reason why I'm curious about the hardness is it's got all this titanium on the outside of it. Titanium conducts heat a lot slower than steel. The worry is that as we quenched this, the heat transfer through the titanium wasn't fast enough to actually cool the steel enough to form martensite, which is the hard microstructure of steel. It appears that it was fast enough. So in this cross-section it works. We'll see how much that changes when we get to that one. We're going to put it in the oven to temper it. And now let's roll this one. Go another millimeter down. Look what I just found. It took me having this thing for 9 months to realize there's a measurement scale on it. It looks like it's still in one piece. Oh! Looking good. Okay, go back up to temperature, then we're gonna let it air cool. Oil hardened after tempering. 57, 58, air cooled sample. 32 Rockwell, definitely softer. Our rolled sample is looking quite promising. However, on this end, we did get a little bit of delamination. You'll see we stretched it almost twice its original length. Let's clean up these edges, then maybe slice it in half.
Well, you say you made it twice the original length, and that's because you did 0.5 strain.
Exactly. Look at you. Well, very good, Jamie. 5 passes, 0.1 strain. Oh, very good. I don't know if I do want to cut it in two, because I can make a sweet little knife out of that fellow if it works, but obviously we're here for experimentation, we're not here for making things.
Yeah, but I thought you liked cutting things in two.
Is that a reference to this? Finest forged tubing, always supplied in 2 halves. It's hot. Now I'm gonna harden and temper this half, see if anything has changed.
After the roll and.
Exactly. There's actually 2 more rollings.
Roll and.
There we go. Air-cooled sample, bending test. Let's go! No way! Did you see that? I'll go again. Look at that! That's awesome! Now our hardened sample. This is gonna be a bit more violent, I suspect. 3, 2, 1. Oh yeah! Wow! Whoa. I don't know what I was hoping for here. Our unhardened piece largely stayed together, which is remarkable. It appears like there's a tiny bit of delamination here on the unhardened piece, but the rest, it all stayed together through these incredible bends. This is hard on the material. Look at that plastic deformation through there as it's taken the bend and it has shrunk the titanium on the tension side. It has upset the titanium on the compressive side, and the joint through there withstood it. That's a remarkably good titanium to steel bond. However, of course, on the hardened piece, it is not surprising that the steel broke. The steel is now in a much more brittle state, so I expect the steel to break when we're trying to force it around a bend that's that tight at 58 Rockwell. And obviously it appears like we also delaminated the steel from the titanium. I might have liked the steel to stay stuck to the titanium a little bit more and maybe force the titanium to break where the steel broke. So instead of the steel breaking and then it peeling as the titanium then takes the bend, I almost would have preferred the steel broke, but the bonds between the steel and the titanium, just either side of where the steel break, would have been so tight that it would have made a stress concentration to the titanium and broken the titanium there. Obviously, our bond between the steel and titanium is not as strong as the steel itself. I think that's what you can deduce from it. Anyway, it's now time to harden that forged piece. So, into the oil you go, and we'll test this one too. This is obviously also going to break, so I'm just going to do a quick temper and get it up to a deep blue or something. Some pretty colors. Here we go! Wow, that was impressive! That was very impressive. Now obviously I tempered it hotter than the previous one. That hotter temper is going to mean that it is now tougher. Oh, do you hear that?
Yeah.
It just popped in my hand. But with it being tougher, it also then gets less hard. That was 49 Rockwell, so a good bit softer than the previous one and not quite hard enough for a knife. Very interesting. These are, of course, very different cross-sections, this one being thinner than that. It means that the bend radius relative to its thickness is smaller or bigger? I don't know. But there's a difference. It takes less stress to bend a small thing than a big thing. What's very exciting about this test is we have shown that the titanium to steel bond can be very, very good, especially in its unhardened state. The fact that that didn't separate is remarkable. We have shown that it's likely not going to perform as well as just a bit of steel. We kind of know that, right? That's why katanas are made of steel and they're not made of titanium with steel. The characteristics of steel suit a sword really, really well. But what I'm thrilled that we've learned is that it is possible to forge it. And when I had the disasters earlier on in this video, I thought the answer was there is no chance of forging it. But at 850 degrees Celsius and 0.1 strain on each pass, we were able to forge it down and stretch it out and not have a significant loss of strength, because we can't even measure the loss of strength because it doesn't look like it, I mean, it looks great. So that means I now have 2 roads ahead of me. I can either heat this up and then roll it down into some thinner bar, or heat this up and then just go straight to a quench. And I don't know what on earth I'm gonna blooming do. Fortunately, I'm definitely gonna need a longer way of heating this stuff. Hang on a second, I'm lost now. This might need a chalkboard here. Might need a flowchart here, Jamie.
Hang on, when you said titanium Damascus katana, did you just mean the slabs of titanium and steel?
No. This is a test before we spend days and days and days making beautiful titanium and beautiful steel Damascus.
So they will both be patterns?
They will both have patterns, yes. If I quench this experiment, what we're demonstrating is that we can bond a big slab that needs to be as long as the finished katana, and we will then heat treat it in its big slab state before we cut out the katana. So with this piece, I would then quench it, and then grind down the sides so that we get it to the final thickness, test it, and if it's good, I'm gonna need a longer kiln to be able to heat up, bond, and heat treat our final katana dimensioned piece. Now, if we want to forge this piece, we can heat and forge. It's currently 49 centimeters. We'll be able to increase its length about that much. That also means we need a longer kiln. Bugger. Okay, I've got the definitive answer. Where did I put it? Where did it go? What have I done? Oh, for goodness sake. Here is the plan. We are going to harden and temper this big slab here, mill down the sides close to the thickness of an actual blade, and then turn it into a chopper and test it and see if it's good enough, or see if the titanium sides fall off. Because now that we know that there doesn't appear to be a massive difference with our new rolling techniques at 850 Celsius, or just bonding it and leaving it from 850 Celsius, I feel like I'm gonna get a picture of the suitability of this whole titanium to steel thing once that becomes a longer, thinner blade and we start abusing it. Out she comes. Temper. Time has passed. Wow, how pretty is that? And it appears like it's all stayed bonded. I'm wrong. We actually have a delamination here. That looks like it's separated there. Oh no, it's definitely separated at the end. Looks good, good. Looks good, just at that one end. It's bloomin' delaminating! Now I'm gonna bring this thickness down. I heard a hell of a noise on this cut. It is not sounding. Oh, that's awful. Oh, no. It couldn't even handle the forces of a milling cut. That is very upsetting. What I was trying to do here was thin down the titanium. The concept being, bond it nice and thick so that we've got some extra stability, and then mill down the titanium to get the final thickness that we would want for a katana, which is about 6 millimeters. That would leave titanium cladding visible, and then as we ground our bevel in, it would then expose the steel core. So in trying to get down to that thickness, we have completely ripped the titanium off of the nickel. And just the cutting forces alone were enough to delaminate the titanium from the nickel here. That is a real tragedy. That split goes all the way up to here. I don't think that'll do for a successful katana. Something tells me it needs to be a better bond than that. What has changed and what has gone wrong? All that I can think to do now is, considering the really remarkable success we had rolling this piece's thickness down, is instead of trying to mill my thickness down on this, maybe we will try and roll the thickness down. It's possible that that rolling is enhancing the bond and making the bond stronger. Again, I can only do so much of it because we only got so much furnace length to play with. But I think this is my last hope now. Roll at 850 to reduce the thickness, get it close to katana thickness, then put a bevel on it and hopefully test its performance and see, is it going to be enough? Woo! Don't break. Only get about one more heat out of it before it's too long. Hard to make good videos when you're sad. Yeah, it's gonna be a real problem here. Because like, if you start saying, oh, I'm gonna make a titanium Damascus katana, and then you can't make the titanium Damascus katana, that's some real noob behavior there. Whoa, that got a bit bendy. Will it fit though? Oh gosh, don't know if that counts as fitting. That's quenched, now we temper, then we test. I'm not feeling good, guys! Not feeling very confident. Now we wait. And the bloody oil leak is back. Still incontinent. Will anything work? Can't even fix an oil leak. Right, now this is only a katana-shaped object. Do remember, we are still very much in the experimentation stage. It's just that since I had a long, thin rectangle, I thought we might as well put a point on it. It gives us some positive reinforcement, reminding us that we're not just making rectangles of steel. Hopefully, eventually, we're going to make a blade. Now, what have we noticed while we were grinding it? Here's our steel, here's our nickel interlayer, and there is our titanium. But have a look at this. Got a few little voids between the nickel and titanium there, here, and there on the other side, which would obviously be unacceptable for a final piece. This is just a test. It's only rough ground. We're going to find out if it'll break. Let's stress test it. That's satisfying. Now remember, even if it survives all this testing, the final goal is to make one that has a Damascus steel core and a titanium Damascus jacket, not just the regular bits of sheet that we've currently made this test piece from. It's hopefully a good example to figure out our processes, but the final piece is going to be a lot more complex. Here we go. Oh, baby. Oh, you hear that noise? Oh! That feels amazing to use. Yeah! It's all still together. No way. I was definitely expecting this thing to pop into pieces, especially with those flaws there. Okay, we keep going. Oh! Oh, baby! That's a big bit of pine. Oh no! It's bending! Hey, a bend is a lot better than a break, let me tell you what. Yes! Well, if it did all that, I'm pretty daunted to say, but I think as far as a proof of concept goes, it is possible to get the titanium stuck well enough to withstand some pretty significant abuse as a sword. The trouble is, our test piece in plain titanium and steel was this long, and we need to make one in titanium Damascus and steel Damascus that is much longer. This is going to be a challenge. Let's now see what happens if we bend it. Will it just split in half, or will it take a bend? In 3, 2, 1. That's awesome! No way! Yes! That's amazing! Now, obviously, we expect it to yield and permanently deform into that bend. It didn't break! I'm gonna need to build or somehow acquire a much larger kiln. I'm absolutely terrified, but I am quite happy holding this lovely example here. Again, shout out to today's sponsor, which was Sawdust. Use code ALEC10 at the link below to get 10% off their Shadow Dancer custom katanas. Buckle up, guys. This is going to be a hell of a ride. Thank you so much. Bye-bye.